Every 30 days, you look up and see it sitting there, calm, familiar, reachable. But the moon's surface hits 450 degrees Fahrenheit in direct light and drops to nearly 300 degrees below zero in the shade. The dust slices through metal. The radiation kills without warning. And there is no air. Anywhere. We have walked on it. We barely survived it. In this video, we go through 33 layers of how genuinely hostile our closest neighbor really is. From glass-sharp dust that hunts you, to craters colder than Pluto, to a radiation blast that gives you 0 seconds of warning. If you enjoy what we do here, a like and subscribe keeps this channel alive. Prepare yourselves. We begin. You have seen it your entire life hanging up there, steady and bright, close enough to feel familiar. That familiarity is the most dangerous thing about the moon. Here is what we actually know. The moon sits roughly 239,000 miles away. In cosmic terms, that is nothing. A weekend drive by the universe's standards. And because we have been there, because humans planted flags and drove rovers and came home alive, something in our brains filed the moon under manageable, explored, known, safe enough. Scientists call this the proximity illusion. The closer something is, the more our brains downgrade the threat. And the moon has been close to us for so long that entire generations grew up treating it as a destination rather than a survival challenge. But here is what a survival challenge actually looks like. Apollo astronauts trained for years. They wore suits that took engineers over a decade to design. They carried enough oxygen for hours, enough water for days, and enough redundant systems to fill a small submarine. And even with all of that, every single mission came within one equipment failure of becoming a catastrophe. Apollo 13 did not even make it to the surface. A single oxygen tank rupture turned a moon landing into a life-or-death scramble, 3 days from home. The astronauts who did land described stepping onto the surface as entering a place that wanted them dead. Those are not dramatic words from a press release. That is the consistent language from mission debriefs, personal journals, and interviews given decades later, when there was nothing left to prove. The moon offers you no margin. On Earth, if your car breaks down in the desert, you can survive for a day or two on the water, in your body. On the moon, if your suit loses pressure, you have roughly 15 seconds of useful consciousness. After that, the vacuum does the rest. And the vacuum is total. No atmosphere means no sound carries. No wind moves. No weather changes. The surface you see in photographs looks still and peaceful, precisely because nothing alive has ever shaped it. Every crater, every ridge, every footprint left by Apollo astronauts in 1969 is still sitting there today, perfectly preserved, because there is nothing on the moon capable of erasing it. That stillness is a warning. A living world changes its surface constantly. Earth reshapes itself through rain, wind, planned routes, and tectonic movement. The moon has none of that. It is frozen in a state of ancient violence, every scar from every impact preserved forever in the silence. Here is a number that reframes everything. The moon receives no protection from the stream of particles and radiation pouring out of our star. Earth's magnetic field and atmosphere absorb and deflect most of that energy before it reaches us. The moon has neither. The surface radiation dose a human being would absorb in a single lunar day exceeds what a radiation worker on Earth is allowed to receive in an entire year. We went there 6 times and called it a triumph. It was. But we also left each time as fast as we possibly could, and no human being has stood on the lunar surface in over 50 years. That gap is not an accident. It is an honest assessment of the problem. The Apollo program proved we could survive the moon in short bursts, with perfect equipment, perfect timing, and a great deal of luck. What it did not prove is that the moon is survivable in any sustained or permanent way. Every chapter ahead pulls back one more layer of what the surface actually does to a human being, a machine, and a plan. And the first layer is the most immediate one. The air is gone. Every consequence flows from that single fact. Step outside on the moon and your suit is the only thing between you and a pressure of exactly 0. 0. The word sounds simple. It is anything except simple. Here on Earth, The atmosphere presses down on your body with about 14.5 pounds of force per square inch. You never feel it because your body pushes back with equal pressure. That balance is something your biology has maintained every second of your life without you noticing. Remove it, and your body does not just struggle, it begins to come apart. In the vacuum of the lunar surface, any exposed liquid boils instantly. Your saliva, the moisture on your eyes, the fluid lining your lungs. A human being exposed to the lunar surface without a suit would not freeze or suffocate first. They would experience something called ebullition, where dissolved gases in the blood and tissue expand outward because there is no atmospheric pressure holding them in. Within seconds, the body swells to roughly twice its normal size. Consciousness goes in about 15 seconds, as oxygen-starved blood fails to reach the brain. The suit prevents all of that, but the suit carries its own set of threats. Apollo suits were pressurized at about 4.5 pounds per square inch, roughly 1/3 of Earth's normal atmospheric pressure. That sounds like enough. In practice, it turned the suit into a rigid balloon. Astronauts reported that simple tasks like picking up a rock or bending their knees required enormous physical effort. After a 6-hour moonwalk, their hands were so fatigued from fighting the suit's resistance that gripping tools became painful. One astronaut compared it to squeezing a fully inflated basketball for 6 hours straight. That physical fatigue matters because fatigue leads to mistakes. And on the moon, a mistake during a suit operation, a missed connection, a cracked seal, a valve turned the wrong way does not give you a chance to correct it. The suit itself is a marvel of engineering. 14 layers of material protect against puncture, thermal extremes, and micrometeorite impact. But 14 layers also means 14 potential failure points per square inch of surface area covering your entire body. The suits, worn during Apollo, were hand-stitched by seamstresses in Delaware, assembled with the same tools used to make bras and corsets, because no industrial machine existed that could stitch the necessary curves with the required precision. Each suit took over 2,000 hours to build, and they were designed to last for roughly 115 hours of use. A permanent lunar presence would require suits that last months or years. No such suit exists. Scientists working on next-generation lunar suit designs confirmed as recently as 2210 that every prototype degrades faster than expected, primarily because of one material the moon produces in terrifying abundance: dust. Razor-edged, electrostatically charged, everywhere at once. But before we get to the dust, something else happens the moment you step outside that almost no one talks about: the silence. On Earth, your body is surrounded by sound at all times: wind, footsteps, the ambient hum of biology and environment. Sound is physical. It reaches you, and your nervous system uses it constantly as a reference signal that the world is real and present. On the moon, outside your suit, there is nothing. Inside your suit, you hear your own breathing amplified and your heartbeat bouncing off the helmet walls. Astronauts reported that the sensory contrast was deeply unsettling in ways they struggled to describe after returning home. One described it as feeling watched by emptiness. That feeling has a physiological basis, and what the moon does to human psychology over extended time is a problem no engineer has solved yet. But even that is secondary to what the ground beneath your boots is actually doing to your equipment right now, starting the moment you land. Stand on the lunar surface and take one step from sunlight into shadow. In that single step, the temperature around you drops by over 400 degrees Fahrenheit. 400 degrees. In one step, on Earth, temperature gradients that dramatic exist only inside industrial furnaces and cryogenic laboratories, with thick insulated walls separating the two environments. On the moon, they exist side by side in open space, separated by nothing except the line where light ends and shadow begins. This happens because the moon has no atmosphere to distribute heat. On Earth, air moves. It carries warmth from hot places to cold ones, softening extremes and creating the relatively stable temperature ranges that life depends on. The moon has no air to do that work. Heat travels only by direct radiation from the star above and direct conduction through the ground beneath your feet. The moment a surface loses line of sight to that light source, it starts losing heat with nothing to slow the process. The result is a world of violent thermal extremes packed into a surface area you could walk across in minutes. In direct sunlight, the lunar surface reaches 250 degrees Fahrenheit. Move into the shadow cast by a boulder the size of a car, and the ground beneath that shadow sits at roughly negative 280 degrees Fahrenheit. Both temperatures exist simultaneously. You could theoretically place one gloved hand in sunlight and one in shadow and expose them to a swing of over 400 degrees at the same time. For human tissue, that range is instantly lethal, without protection. For equipment, it is a slow and relentless destroyer. Metal expands in heat and contracts in cold. Every piece of hardware on the lunar surface cycles through this expansion and contraction every time it moves between light and shadow, and again every lunar day as the 2-week-long period of sunlight gives way to 2 weeks of darkness. Apollo scientists confirmed that this thermal cycling caused materials to crack, seals to fail, and mechanical connections to loosen in ways that ground testing in vacuum chambers failed to fully predict. The lunar roving vehicle used during the later Apollo missions was designed and tested exhaustively before launch. On the surface, its wheels began warping from thermal stress within the first few hours of use. The vehicle still functioned, but engineers watching from Earth noted deformations they had not anticipated and could not fully explain until years of post-mission analysis. Now, imagine a permanent habitat on that surface. Every wall, every seal, every pipe and wire inside that structure cycles through the same stress twice per lunar month for years. Materials that engineers certify for 500 thermal cycles begin degrading long before you reach 500 lunar months of habitation. There is an engineering approach being studied to address this. Burying structures beneath several feet of regolith, the loose rocky soil covering the moon's surface, provides insulation and thermal stability. The ground a few feet down maintains a nearly constant temperature of about negative 30 degrees Fahrenheit, which is cold, but manageable, and critically, stable. Stable is survivable, but digging into lunar regolith carries its own set of problems that researchers are still working through. And thermal extremes on the surface do something else that almost no mission planning document addresses directly. The boundary between light and shadow on the moon shifts constantly as the moon rotates. A habitat sitting in comfortable shadow at one point in the day may be in full baking sunlight 12 hours later. Managing that shift, predicting it, building around it, adds a layer of engineering complexity that grows with every day a crew spends on the surface. This is confirmed physics, and the engineering solutions are years from being tested in the real environment. The temperature alone would make the moon one of the most hostile surfaces in the inner solar system. But the temperature is only the third item on this list. What comes just below the surface is stranger and more dangerous than the heat. The moon rotates slowly, extraordinarily slowly. One full rotation of the moon takes about 29.5 Earth days. That means one lunar day, from sunrise to sunset, lasts roughly 14.5 Earth days. And then the night begins. Another 14.5 days of total darkness. For humans, this is a survival problem on a scale that most mission planning documents underestimate. During the 2-week lunar day, solar panels work. They generate electricity, charge batteries, power life support, heat the habitat, run communication systems. The energy budget of a lunar base during daytime is manageable. Difficult, but manageable. Because the star above is pouring out power constantly, and the absence of atmosphere means every photon arrives at the panel without being filtered or scattered. Then the night comes. For 14.5 days, there is no sunlight at all. Temperatures plunge to nearly negative 280 degrees Fahrenheit across the open surface. Any battery system powerful enough to run a lunar habitat through an entire lunar night would need to be so large and heavy that launching it from Earth becomes economically impossible with current technology. Scientists have calculated that powering even a small habitat through a single lunar night using batteries alone would require a battery pack roughly the size of a city bus, just for basic life support. Nuclear power is the confirmed alternative. A small nuclear fission reactor can generate electricity independent of sunlight, running continuously through the night and providing thermal energy to keep systems from freezing. The National Aeronautics and Space Administration and the Department of Energy jointly developed a concept called kilopower, a small fission reactor designed specifically for lunar and deep space use. Tests in Nevada in 2018 confirmed it could generate stable power for over 2 years. But a nuclear reactor on the moon introduces its own set of complications: radiation shielding, thermal management in vacuum, maintenance by astronauts in pressurized suits with limited dexterity, safe disposal of radioactive material in an environment with no waste infrastructure. And here is what makes the 2-week night even more disorienting for human biology. Your body runs on a 24-hour circadian rhythm. Every cell in your body, every hormone cycle, every sleep-wake signal is calibrated to a day that lasts 24 hours. On the moon, a single day lasts 708 hours. Studies on Earth of people isolated in environments with no natural light cues show that circadian disruption begins within days. Cognitive performance drops. Emotional regulation becomes harder. Sleep becomes fragmented and unrestorative. Immune function weakens. On a 14-day lunar night, with no sunrise to anchor the body's internal clock and no natural temperature variation to reinforce the cycle, the biological disruption would be severe and compounding. Researchers studying long-duration space missions call this chronobiological stress, and it is considered one of the top 3 psychological risks for crews spending extended time in space. The other 2 involve isolation and radiation. The moon delivers all 3 simultaneously. There is one location on the moon that partially escapes the night problem. Certain peaks near the lunar poles, the ones tall enough to sit above the surrounding terrain, receive near-constant sunlight as the moon rotates. Because the angle of incoming light at the poles is so shallow that these peaks stay illuminated even as the ground around them cycles through darkness. Scientists call them peaks of eternal light. They sound like a solution, and in one narrow sense they are. But what surrounds those peaks is something that makes the 2-week night feel straightforward by comparison. Apollo astronauts did not expect the dust to be the biggest problem. They expected the vacuum, the radiation, the temperature. Those were the threats in the mission briefings, the ones that engineers had spent years designing solutions for. The dust was considered an inconvenience, a minor operational concern. Within the first few hours on the surface, it became clear they had badly miscalculated. Lunar dust is called regolith. It covers the entire surface of the moon in a layer ranging from a few feet to over 60 feet deep, depending on location. The product of 4.5 billion years of micrometeorite impacts, grinding the surface rock into progressively finer and finer particles. The finest of those particles are smaller than 1 micrometer across. For comparison, a single human hair is about 70 micrometers wide. Lunar dust particles are 70 times smaller than that. But the size is not the primary danger. The shape is. On Earth, particles get rounded over time. Wind, water, and contact with other particles knock off sharp edges and smooth surfaces through a process called weathering. The moon has no wind, no water, no weathering of any kind. Every particle of lunar dust retains the exact jagged, angular glass-like shape it had the moment it was created by an impact. Under a microscope, lunar dust looks like a pile of tiny broken glass shards, because that is essentially what it is. Silicon dioxide fractures with sharp edges, and those edges never dull. When Apollo 14 astronaut Edgar Mitchell returned to the lunar module, after his moonwalk, he noticed the dust clinging to his suit was cutting microscopic scratches into his helmet visor. The material of the visor was rated to withstand micrometeorite impacts. Dust was scratching it. Equipment degradation began faster than mission planners had modeled. The seals on sample containers became difficult to close because dust particles wedged into the gaps and prevented a clean connection. Zippers on equipment bags began sticking. The joints on the lunar roving vehicle's wheels showed accelerated wear. Every moving mechanical part that touched the surface showed damage that exceeded pre-mission predictions. And then there is what happens when the dust reaches the lungs. During Apollo 17, astronaut Harrison Schmitt experienced what he described as lunar hay fever within minutes of removing his helmet inside the lunar module. Sneezing, throat irritation, eyes watering. His symptoms were caused by dust particles that had entered the cabin on his suit and become airborne in the pressurized interior. Schmidt's symptoms faded after a few hours. Short exposure to a tiny quantity caused measurable respiratory irritation. Scientists studying the long-term effects of lunar dust exposure on lung tissue found that, unlike terrestrial dusts which the lung can partially clear over time, the jagged shape of lunar dust particles physically embeds into lung tissue and stays there. The particles are also chemically reactive because they have never been exposed to water or oxygen. When they contact biological tissue for the first time, they trigger an inflammatory response that does not resolve. Extended exposure to lunar dust over weeks or months would cause a condition researchers compare to silicosis, a progressive and irreversible lung disease. And removing the dust is nearly impossible. Its electrostatic charge makes it cling to every surface. Brushing it spreads it. Vacuum systems clog. Filters saturate. Engineers designing the next generation of lunar habitats list dust mitigation as the single most unsolved engineering problem in the entire program. And the dust does something else. Something active. Something that researchers confirmed and that almost no one outside the scientific community knows about. The dust does not just sit on the surface, it moves. Scientists confirmed this in the 1970s using data from the Surveyor landers, and later through observations from lunar orbiters and surface experiments left behind by Apollo missions. A faint layer of dust particles hovers above the lunar surface at all times, suspended in the air that does not exist. The mechanism that drives this is electric charge. The lunar surface carries an electrical charge. On the day side, ultraviolet radiation from our star strips electrons from surface particles, leaving them positively charged. On the night side, the surface accumulates electrons from the surrounding plasma environment of space, leaving it negatively charged. At the boundary between day and night, where these two charge regions meet, the electric field becomes intense enough to launch dust particles off the surface and send them traveling horizontally across the terminator, the line dividing lunar day and night. Laser measurements from lunar orbiters have detected a persistent haze of fine particles extending up to several miles above the surface near the terminator. The dust is not drifting. It is being actively propelled by electric fields that shift and strengthen as the terminator moves. For a lunar base, this matters enormously. Any surface near the terminator, which sweeps across the entire moon twice per lunar month, experiences a wave of electrostatically charged dust that clings to solar panels, coats optical instruments, and penetrates mechanical seals. Apollo mission records documented a consistent drop in the efficiency of solar-powered equipment as dust accumulated. Even a thin coating of lunar dust on a solar panel reduces its energy output significantly. Astronauts on extended missions could not step outside and wipe the panels clean without creating new contamination. Every contact with a dusty surface transfers particles. Every transfer creates new contamination pathways. But the dust problem deepens further when you consider what happens during landing and takeoff. A descending spacecraft kicking up lunar regolith at high velocity does not produce a dust cloud the way it would on Earth. On Earth, air resistance slows particles and gravity pulls them back down quickly. On the Moon, particles launched by rocket exhaust travel in ballistic trajectories with nothing slowing them. High-velocity dust particles can travel miles in every direction from a landing site. Scientists calculated that a spacecraft landing near an existing habitat would sandblast every exposed surface within range at speeds exceeding several hundred miles per hour. The abrasion from a single nearby landing event could damage solar panels, scratch optical sensors, and degrade the outer layers of a habitat's thermal insulation. Multiple supply landings over the course of a year-long crewed mission would cause cumulative damage that mission planners have not fully accounted for in current design proposals. There is a proposed solution involving electrostatic shields, essentially charged surfaces that repel incoming dust particles using the same electric forces the Moon uses to move them. Laboratory tests showed partial effectiveness. Field tests on the actual lunar surface have not happened yet. Whether electrostatic shielding works in the complex and variable charge environment of the real lunar surface remains an open question. And while dust dominates the surface environment, it shares that environment with something moving at a speed that makes dust particles look slow. What hits the moon from above, constantly, silently, and without warning, carries enough energy to punch through steel. The moon is under constant bombardment. Every second of every day, tiny fragments of rock and metal, traveling at speeds between 11 and 45 miles per second, slam into the lunar surface. These are micrometeorites, particles ranging in size from a grain of sand down to a speck of dust. And they arrive from every direction because the moon has no atmosphere to protect it. On Earth, the vast majority of these particles burn up harmlessly in the upper atmosphere. Friction with air molecules slows them and heats them to temperatures that vaporize everything except the largest fragments before they reach the ground. You have seen this process from the ground. Shooting stars are micrometeorites burning up tens of miles above your head. The moon offers no such protection. Every particle that reaches the lunar vicinity hits the surface at full velocity. At 11 miles per second, a particle the size of a grain of rice carries enough kinetic energy to vaporize itself, and a volume of surrounding rock hundreds of times larger than itself on impact. The energy release creates a tiny explosion that melts surrounding rock into glass and sprays molten droplets in all directions. Over billions of years, this process is what created the glass-edged structure of lunar dust particles. Scientists calculated the rate of micrometeorite impacts on the lunar surface using data from sensors left by Apollo missions and from orbital surveys. The confirmed average rate across the entire lunar surface amounts to roughly 1,000 tons of material added per year from infalling particles. Most of that mass arrives in particles too small to see without a microscope. But the energy those particles carry is real, measurable, and damaging. For a habitat, the concern is not a single catastrophic impact from a large object. Engineers can design walls thick enough to stop most meteoroids above a certain size. The concern is cumulative degradation from thousands of micrometeorite strikes per square meter of exposed surface per year. Each strike is individually tiny. Collectively, they sandblast exposed materials at a rate that degrades thermal insulation, scratches optical surfaces, and weakens structural integrity over time. Here is how to picture the scale of this. Imagine leaving a new car outside in a sandstorm for a year. The individual grains of sand are tiny. None of them alone causes significant damage. After a year, the paint is gone, the windows are scratched, and the surface has aged visibly. Now run that sandstorm at thousands of miles per hour and never let it stop. That is the micrometeorite environment on the lunar surface. The Apollo suits were rated for the micrometeorite environment during short surface excursions lasting a few hours. Over the course of a 6-hour moonwalk, a suit accumulated measurable impact damage that engineers recorded and studied post-mission. The damage was considered acceptable for short stays. For suits used repeatedly over months, the cumulative damage would eventually compromise protection. No suit material currently in development has been confirmed to maintain full protective capability through a year of regular use on the surface. The engineering target exists. The material to meet it does not yet, and micrometeorites bring another threat with them that compounds everything already on this list. Every impact, every vaporization event, sprays material into the lunar environment. That material includes heavy metals, complex mineral compounds, and in some cases, organic chemistry from the impacting particles themselves. The chemical environment at the lunar surface is therefore not static. It changes constantly as new material arrives and mixes with existing regolith. That chemical complexity matters for life support systems, for water extraction plants, and for any biological process intended to run in or near the lunar surface. But the threat arriving from above is not limited to particles you cannot see. The radiation environment is a different category of problem entirely, and it is one that no wall, no suit, and no engineering solution has fully solved. Stand on the moon, and you are standing inside a radiation environment that would kill an unprotected person within days. This is confirmed. Instruments carried by the Lunar Reconnaissance Orbiter and by the Chang'e lunar landers measured the radiation dose on the lunar surface directly. A person standing on the moon with no protection would absorb a radiation dose roughly 200 times higher than a person standing on the surface of Earth on any given day. Radiation in space comes from two primary sources, and each one damages human tissue in a different way. The first source is our star. It constantly streams charged particles outward in all directions, a flow called the solar wind. Under normal conditions, this stream carries a radiation dose that is manageable with appropriate shielding, but our star is active. It produces events called solar particle events, sudden eruptions that release enormous quantities of high-energy particles in a matter of hours. On Earth, the magnetic field and atmosphere deflect the vast majority of these particles before they reach the surface. On the Moon, a solar particle event hits full strength with nothing between you and the source. The second source comes from outside our solar system entirely. Galactic cosmic rays are high-energy particles accelerated by supernovas and other violent events across the galaxy. They arrive from every direction simultaneously at nearly the speed of light, and they carry enough energy to pass through several feet of solid rock. Standard aluminum spacecraft walls stop them partially. Dense materials like polyethylene do better, but no shielding that a human mission can practically carry stops galactic cosmic rays completely. Here is what galactic cosmic rays actually do to a human body. When a high-energy particle passes through living tissue, it does not simply deposit energy the way lower-energy radiation does. It physically severs the double helix of deoxyribonucleic acid molecules in cells it passes through. The cell's repair mechanisms can fix most of this damage if the exposure rate is low. But at lunar surface radiation levels, the rate of damage exceeds the rate of repair over time. The accumulated damage increases cancer risk and, over longer exposures, degrades the central nervous system. Apollo astronauts reported seeing flashes of light with their eyes closed during lunar transit, caused by cosmic ray particles passing directly through their optic nerves. This is confirmed. The phenomenon was documented and studied. The particles they were seeing were traveling through their heads. Scientists studying data from the Apollo missions found elevated rates of cardiovascular disease among astronauts who flew to the Moon, compared to those who flew only to low Earth orbit. A study published in 2016 found that lunar astronauts died from heart disease at roughly 4 times the rate of astronauts who stayed closer to Earth. 4 times. The study was criticized for its small sample size, and further research is ongoing, but the directional signal from the data is consistent with what the physics predicts. The radiation environment beyond Earth's magnetic shield accumulates damage in the human body in ways that medical science can measure and is only beginning to fully understand. And the radiation problem contains a feature that makes it uniquely terrifying compared to every other hazard on this list. Most threats give you some warning. Temperature is measurable, dust is visible, micrometeorites leave marks, radiation is invisible, odorless, and silent. You cannot feel it as it works through you. By the time biological symptoms appear, the damage has been accumulating for days, weeks, or months. And one specific type of radiation event gives you no warning at all. It moves at nearly the speed of light, and by the time your instruments detect it, it is already hitting you. There is a type of solar event that can kill an astronaut on the Moon before mission control has time to send a warning. It is called a solar particle event, and the most powerful versions, called solar proton events, release enough radiation in a matter of hours to deliver a lethal dose to an unshielded person. Here is how fast it happens. Our star is approximately 93 million miles away from Earth. Light and the fastest particles released in a solar eruption cover that distance in about 8 minutes. On Earth, forecasters using solar observatories can sometimes detect the precursor signals of a major eruption before the particle wave arrives. Sometimes they have an hour of warning, sometimes minutes. The warning window is never guaranteed. For astronauts on the lunar surface, 8 minutes is not enough time to get inside a habitat, let alone reach any meaningful shielding. A crew conducting a scheduled 6-hour moonwalk would need to be within reach of immediate shelter at all times, and that shelter would need to be thick enough to significantly reduce the particle dose. Current habitat designs include dedicated storm shelters, small, heavily shielded rooms where crew members can wait out a solar particle event. But there is a critical problem with storm shelters. A solar particle event can last anywhere from a few hours to several days. Sitting in a small shielded compartment for 72 hours while a radiation storm passes with limited food, water, and movement, while mission time drains away outside, is a scenario that has no comfortable solution. Scientists studying the solar cycle confirm that solar particle events are more frequent and more intense during periods of high solar activity. Our star operates on an approximately 11-year cycle, moving between solar minimum, when activity is low, and solar maximum when eruptions are frequent and powerful. The next solar maximum is projected to peak around 2025, which means any near-term crewed lunar mission would operate during some of the most active solar conditions in over a decade. The confirmed lethal dose from a major unshielded solar proton event is achievable in under an hour. Astronauts in a standard spacesuit on the lunar surface during a major event would receive incapacitating radiation exposure before most storm shelter protocols could be completed. This is why the radiation environment is treated differently from other moon hazards in mission planning. Most hazards are mechanical. They have engineering solutions, materials that block them, systems that manage them. Radiation penetrates most materials. The only reliable shield against the highest energy particles is mass, either the mass of a planet's atmosphere and magnetic field, or an equivalent mass of shielding material. To shield a lunar habitat to the radiation standards applied to workers in nuclear power plants on Earth, engineers calculated you would need walls made of polyethylene roughly 16 inches thick surrounding the entire structure. The mass required to launch that much shielding from Earth is currently beyond any single rocket program's capacity. The practical alternative is to build habitats partially underground, using the moon's own regolith as shielding. Several feet of compacted lunar soil above a habitat reduces radiation exposure significantly. The physics confirms this approach works. The engineering challenge of building and sealing an underground habitat on the moon without Earth-based construction equipment and with crews in pressurized suits remains unsolved. And even underground, the second radiation source, the galactic cosmic rays arriving from every direction simultaneously, passes through the regolith and accumulates in the bodies of anyone living beneath it. The radiation problem has no complete solution. Every proposed answer is a partial answer. And living with partial answers in an environment that never stops trying to kill you is its own psychological challenge. One that scientists have started studying seriously because the moon's silence and isolation do something to the human mind that no training program fully prepares a person for. 3 days into the Apollo 11 mission, Michael Collins was alone. Armstrong and Aldrin had descended to the surface. Collins remained in the command module, orbiting the moon every 2 hours. And for 47 minutes of each orbit, he passed behind the moon's far side and lost all contact with Earth. No radio, no signal, no voices. Complete and total isolation in a capsule the size of a large closet, roughly 250,000 miles from another human being. Collins later described those moments as peaceful. Genuinely peaceful, he said, in a way that surprised him. He was the most isolated human being in recorded history, and he was okay. Most people would not be. Scientists studying the psychological effects of isolation, confinement, and sensory monotony on human beings use data from Antarctic research stations, submarine crews, and simulated Mars missions to model what happens to a mind over weeks and months of this kind of environment. The consistent finding is that the psychological degradation is real, measurable, predictable, and in some cases irreversible. The moon adds a layer that no Earth-based simulation captures. You can see Earth from the lunar surface. It hangs in the sky, a blue and white sphere about 4 times the size of the full moon, as seen from Earth. It is right there. Every person you have ever known, every place you have ever been, the entire context of your existence, visible in the sky and completely unreachable. Researchers call the emotional response to this overview effect. Astronauts who have seen Earth from the moon or from low orbit report a consistent shift in perspective that is partly transcendent and partly destabilizing. The smallness of Earth against the surrounding void, the recognition of how thin the atmosphere is, the understanding that everything human civilization has ever done happened on that single visible sphere, produces an emotional response that ranges from profound calm to quiet terror. On extended lunar stays, the Earth would be a constant visual presence. Scientists studying crew psychology for long-duration missions believe that daily visual exposure to Earth, combined with the inability to return, would function as a chronic psychological stressor over time. You can see home. You cannot reach it. That gap between visibility and accessibility is psychologically distinct from simply being far away. And the moon's environment removes the small psychological anchors that humans use to maintain stability. On Earth, you have weather, seasons, the sound of wind, the smell of rain, biological cues that the world is alive and in motion around you. On the moon, every day is identical to the last in terms of sensory input. The same grey surface, the same black sky, the same distant Earth, the same temperature-controlled air inside the habitat, the same faces across the same table. Psychological studies of Antarctic crews, who experience comparable isolation and environmental monotony during winter-over periods, document a predictable set of symptoms that emerge around the 3-month mark. Irritability increases. Sleep quality drops. Cognitive performance on complex tasks declines. Small interpersonal conflicts that would be easily resolved in a normal environment escalate. At least one Antarctic winter-over incident involved a crew member attacking another with a hammer over a chess game. On the moon, there is no emergency evacuation. If a crew member becomes a danger to themselves or others, mission control cannot send help. The crew must manage the situation inside their habitat with whatever psychological resources they have. No mission lasting more than a few weeks has yet confronted this challenge in the lunar environment. Every long-duration plan on paper acknowledges the psychological risk. Every plan also lacks a fully tested solution, and the moon itself, the ground beneath the habitat, adds one more threat to the list that geologists discovered only after analyzing the seismic data the Apollo missions left behind. Apollo 11, 12, 14, 15, 16, and 17 all left seismometers on the lunar surface. They were designed to detect impacts and any geological activity, and the expectation before the missions was that the moon would register as essentially quiet, ancient, geologically dead, stable. The data came back strange. Regularly, predictably, and in ways that Earth's seismology had no framework to explain at first. Researchers identified 4 distinct types of moonquakes in the Apollo data. 2 of them were expected: shallow quakes caused by meteorite impacts, and a second type caused by thermal expansion as the surface heats during lunar day. Both made physical sense and registered as brief, sharp events. The other 2 were surprises. Deep moonquakes originate roughly 700 miles beneath the surface, far deeper than any earthquake, and occur in regular rhythmic patterns, tied to the gravitational tug of Earth as the moon moves through its orbit. Hundreds of distinct deep moonquake locations have been mapped from the Apollo data. They activate and deactivate on regular schedules, like geological clockwork, driven by tidal forces from Earth above. The 4th type was the one nobody predicted: shallow moonquakes. These occur within the top 100 miles of the lunar crust. They are genuinely tectonic in origin, and they are powerful. Compared to the moon's small size, some of the shallow moonquakes recorded by Apollo seismometers would qualify as major earthquakes if they occurred on Earth. And they last for an extraordinary amount of time. On Earth, the rock that transmits seismic waves is saturated with water. Water acts as a dampener, absorbing wave energy and shortening the duration of shaking. The moon has no water in its crust. Lunar rock is cold, dry, and fractured, which means seismic waves bounce through it without dampening for far longer than they would on Earth. Apollo seismometers recorded moonquakes that lasted over 10 minutes. An earthquake of equivalent strength on Earth would stop shaking within seconds. A moonquake rattles on and on and on, as the energy ricochets through dry, waterless rock with nothing to absorb it. Here is how to picture that. If you have ever felt an earthquake, you know that even a moderate one feels alarming because the ground, the thing you depend on for stability, becomes unpredictable. Now extend that feeling for 10 minutes in a sealed, pressurized habitat, where any structural failure means the air you breathe rushes out into the vacuum. The structural requirements for a lunar habitat to survive repeated moonquakes while maintaining pressure integrity are significantly more demanding than the requirements for a building on Earth that must only survive earthquakes. Every joint, every seal, every connection point must flex without cracking, under repeated loading cycles, in a vacuum, in extreme temperature variations, across years of habitation. No such structure has been built and tested. The engineering specifications exist on paper. The ground shaking also affects the one element of lunar infrastructure that seems straightforward: roads. Any carefully leveled and prepared surface between a habitat and a landing zone would be disrupted by moonquakes and need constant maintenance, again in suits, again in a vacuum, again with limited dexterity and limited time. And the seismic data revealed something else about the moon's interior that changed how scientists understand the moon entirely. Something is still active down there, and what that activity implies about the moon's history reframes everything we thought we understood about how it formed. Gravity on the moon is about 1/6 of what you experience standing on Earth right now. That sounds like an advantage. Astronauts bouncing across the surface in long, low arcs, lifting rocks that would be immovable at home, moving through a world that feels light and open. The footage from Apollo missions made it look almost playful. The reality underneath that footage is more complicated, and over weeks and months, on the surface, lunar gravity becomes one of the more insidious dangers on this list. Your body on Earth is constantly fighting gravity. Your heart pumps blood upward against gravitational pull. Your bones maintain their density in response to the mechanical load of carrying your weight. Your muscles, particularly in your legs and core, fire constantly throughout the day just to keep you upright and balanced. Your inner ear, the system that tells you which way is down, is calibrated to Earth's gravitational field. Remove the load, and the body begins dismantling the infrastructure it no longer needs. In microgravity, the zero-gravity environment of the International Space Station, bone density loss runs at roughly 1 to 2% per month in the spine and hip. Muscle mass decreases at a similar rate. The heart, no longer working as hard to pump blood against gravity, begins to weaken and shrink. Fluid shifts upward in the body, congesting the sinuses and temporarily changing the shape of the eye, which alters vision in ways that some astronauts report persist after returning to Earth. Lunar gravity at 1/6 of Earth's creates a middle situation. More load than microgravity, far less than Earth. Research on what this specific gravitational level does to human physiology over months is limited, because no human being has spent extended time in 1/6 gravity. The available data comes from modeling, from animal studies, and from extrapolation based on what happens at zero gravity. The best current models suggest that bone and muscle loss in lunar gravity would be slower than in microgravity, but still significant over months. After 90 days on the moon, an astronaut's bone density might have dropped by a few percent, enough to increase fracture risk significantly. On a surface where falling is easy and medical care is primitive, a broken bone is a mission-ending event. And then comes the return to Earth. An astronaut who has spent months adapting to 1/6 gravity and lands back on Earth faces a body that has partially unlearned how to function in full gravity. Standing up causes blood pressure to drop sharply because the cardiovascular system has deconditioned. Muscles that atrophied cannot support the body's full weight safely. The reintroduction of full gravity on a deconditioned body carries a real risk of injury during what should be the safest moment of the mission, the moment of arrival home. Exercise protocols on the International Space Station are aggressive for exactly this reason. Astronauts spend 2 hours every day on resistance equipment to slow the degradation. But 2 hours of exercise per day in lunar gravity may not be sufficient to maintain Earth-compatible fitness. And 2 hours less of productive mission time per crew member per day over a year-long stay represents a significant operational cost. There is another dimension to lunar gravity that mission planning rarely discusses directly. 1/6 gravity means that the moon holds you down just enough to trap you, while providing almost none of the stability benefits that Earth's gravity gives your body and your movement. And the terrain that gravity holds you to is far more dangerous than it looks from above. The moon is small. Its diameter is roughly 100 miles, about 1/4 the diameter of Earth. That smaller size has a direct and dangerous consequence for anyone walking on its surface. The horizon is close. On Earth, standing in a flat, open area, the horizon sits about 3 miles away. The curve of the planet is gradual enough that you can see it, plan around it, and navigate by it. Roads, trails, and landmarks extend across that visible distance in ways that give you reliable spatial context. On the Moon, the horizon is only about 1.5 miles away. That might sound like a reasonable distance until you consider what lies beyond it. Because the surface curves away faster than on Earth, features that are just beyond the horizon are completely invisible. A cliff edge 1.5 miles away from you looks from your position exactly like flat ground fading into the black sky. You cannot see the drop until you are close enough to the edge that stopping may no longer be possible on loose regolith. Apollo astronauts training for surface navigation were warned about this specific hazard repeatedly. On Earth, navigators use distant landmarks, mountain ranges, city skylines, visible geographic features to orient themselves across long distances. On the Moon, the close horizon eliminates most of those reference points, and the uniform grey color of the regolith makes distinguishing one area of terrain from another remarkably difficult. During Apollo 14, astronauts Alan Shepard and Edgar Mitchell set out on foot to reach a crater called Cone Crater, which lay about 1.5 miles from their landing site. The science return from reaching the crater rim was considered high value because the impact had excavated deep rock layers that were otherwise inaccessible. They climbed toward the crater for several hours, navigating across rolling hills on a surface where every slope looked similar to the last. They came within 60 to 100 feet of the crater rim without realizing it. The close horizon and the monotonous terrain had disoriented them completely. They never reached the rim they were looking for. Later analysis using satellite imagery showed how close they had come. For a crew on a longer mission covering greater distances, this navigation problem scales badly. A rover moving at a rover's speed, covering miles of terrain in hours, approaching features that only become visible within a mile, on a surface with loose granular regolith that reduces braking effectiveness, faces a genuine cliff detection problem that ground-based mission control cannot fully solve from 239,000 miles away with a communication delay. The one-way communication delay between Earth and Moon is about 1.25 seconds. That sounds small. In a ground vehicle, approaching an edge at 15 miles per hour, a 1.25 second delay in receiving a warning from mission control means you have traveled another 27 feet before the warning arrives. Engineers are developing autonomous navigation systems for lunar rovers that do not depend on Earth-based guidance. Terrain mapping from orbit helps, but orbital maps have resolution limits, and the features that matter most for safety, a loose slope, a shallow angle cliff edge, a region of particularly soft regolith, often fall below the resolution threshold of current mapping technology. And those maps were not made for the coldest places on the Moon, the places that sit in permanent shadow, where the terrain has never been photographed in visible light, because visible light has never reached it. What waits in those permanently dark craters is both a resource and a death trap, and the boundary between the two is narrower than any mission planner would like. At the Moon's poles, the geometry of its orbit creates something that should not be possible this close to our star. The Moon's rotational axis is tilted only about 1.5 degrees relative to its orbital plane. That is almost perfectly upright compared to Earth's 23.5-degree tilt. The result is that sunlight at the Moon's poles arrives at an extremely shallow angle, almost horizontal. It can illuminate the tops of crater rims and surrounding highlands, but the interior floors of deep polar craters sit in permanent shadow. Permanent means permanent. Some of these crater floors have not received a single photon of direct sunlight in over 2 billion years. Without any sunlight and without any atmosphere to redistribute heat from the rest of the lunar surface, these crater floors have cooled to temperatures that rank among the coldest surfaces in the solar system. Measurements from orbiting spacecraft confirmed floor temperatures as low as -410 degrees Fahrenheit in some locations. For context, Pluto, the dwarf planet at the outer edge of the solar system, averages about -375 degrees Fahrenheit on its surface. Certain craters at the Moon's south pole are measurably colder than Pluto. These are called permanently shadowed regions, and they sit less than 15,000 miles from some of the most sunlit terrain on the Moon's surface. The temperature contrast between a sunlit peak and the floor of a nearby shadowed crater exceeds 600 degrees Fahrenheit, across a distance you could walk in a few hours. For any mission planning to use polar resources, this temperature contrast is a fundamental engineering barrier. Any rover or astronaut descending from a sun-warmed surface into a shadowed crater would experience thermal stress similar to entering a cryogenic storage facility from a hot desert. Materials contract. Electronics designed to operate in cold environments can still fail below certain threshold temperatures. Lubricants used in rover joints freeze solid at temperatures well above those found in permanently shadowed region floors. The Lunar Reconnaissance Orbiter and ground-penetrating radar instruments mapped the interiors of these craters and found something that changed the entire strategic calculation for returning to the moon. Water. Confirmed. Sitting at the surface and buried just below it, in concentrations high enough to be potentially extractable. The total volume of water, ice locked in lunar polar craters, is estimated in the billions of tons. That water ice is the most valuable resource on the moon. Water can be split into hydrogen and oxygen for rocket propellant. It can be processed into drinking water and breathable air. The presence of accessible water ice at the moon's poles transforms the economics of a permanent lunar presence. A crew that can extract and process local water does not need to launch every drop of water from Earth, which is currently the most expensive item on any lunar mission manifest. But reaching that water ice safely is a problem that current technology has not solved. To drive a rover into a permanently shadowed region, you need a rover that can function at -400 degrees Fahrenheit. No such rover exists. Current planetary rovers operate down to about -40 degrees Fahrenheit before systems begin failing. The gap between that capability and the actual environment in the coldest craters is enormous. And the crater floors present another hazard that thermal engineering alone cannot address. The ground itself in these regions behaves differently from anywhere else on the moon. The permanently shadowed craters at the moon's south pole hold water ice. That is confirmed science. Instruments on multiple spacecraft detected it, mapped its distribution, and estimated its depth. Getting to it is a different problem. The regolith inside permanently shadowed craters is unlike the surface material anywhere else on the moon. Because these floors have never warmed above a certain temperature, the water ice that formed there over billions of years did not deposit as a clean layer. It mixed with the surrounding dust and rock particles as they fell into the crater over time, creating a material that researchers call pore ice, water molecules frozen into the tiny gaps between individual regolith grains. The resulting mixture behaves under load like a combination of very cold sand and very brittle concrete. A rover rolling across it would encounter unpredictable variation in surface hardness. Some areas may support the vehicle's weight. Others may be structurally compromised by the ice content and collapse under load, trapping or toppling the rover in a location where rescue is impossible. Drilling into the surface to extract ice-rich regolith requires a drill that can handle both the extreme cold and the mechanical hardness of frozen mineral ice mixtures. Standard rotary drilling equipment used on Earth for ice core extraction was designed for much warmer temperatures and softer materials. Adapting drill technology for this environment is an active area of research with no confirmed working prototype yet. And then there is the extraction problem. To get water out of the pore ice mixture, you need to heat the material enough to sublimate the ice directly from solid to gas, collect that vapor, and condense it into liquid water. This requires energy, significant energy, in a location that receives no sunlight. The power for this process must come from somewhere else, either from cables running from a solar array positioned on a nearby sunlit peak, or from a nuclear power source brought into the crater. Running power cables from sunlit terrain into a permanently shadowed crater is a solved engineering problem in principle. In practice, the cable must traverse terrain that has never been imaged at high resolution, cross temperature gradients spanning hundreds of degrees, and survive the mechanical stress of thermal expansion and contraction across those gradients indefinitely. Scientists studying the logistics of polar ice extraction proposed a different approach. Rather than driving into the shadowed craters, they suggest using a smaller robotic system that operates inside the crater, while being controlled by a larger rover sitting just outside on the rim, in sunlight, within communication range of Earth. The concept is called a tethered exploration vehicle, and it solves the power problem by connecting the interior robot to an exterior power source via a physical cable. It partially solves the communication problem by relaying signals through the rim-mounted rover. What it does not solve is the navigation and terrain assessment problem inside the crater, where ground truth data remains minimal. Every one of the technical challenges described here is being actively worked on. The solutions are in development. The timelines for those solutions are measured in years to decades, with significant uncertainty at each step. And the polar regions, despite their complexity, are still considered more accessible than the one part of the moon that is completely cut off from Earth by physics itself. No radio signal, no laser communication, no emergency call of any kind can reach you once you cross behind it. Turn the moon around, and you find something the near side never shows you. The moon is tidally locked to Earth. One face always points toward us, and the opposite face always points away. This is a confirmed orbital mechanic caused by gravitational interaction over billions of years. The near side, the one with the seas of ancient lava and the craters you see on a clear night, faces Earth perpetually. The far side, rougher, more heavily cratered, and with a thicker crust, never does. From the far side of the moon, Earth is invisible. More than invisible. No signal of any kind originating from Earth can reach a person or a vehicle on the lunar far side. Radio waves travel in straight lines. The bulk of the moon, roughly 2,000 miles of solid rock, stands between any transmitter on Earth and any receiver on the far side. There is no bending, no diffraction, no atmospheric scattering that brings signals around the obstacle. A crew member standing on the lunar far side is, by the laws of physics, in complete communication blackout with Earth. This makes the far side both scientifically extraordinary and operationally terrifying. The scientific value is real. Without Earth's constant electromagnetic noise, radio waves from the far side of the moon reveal a view of the universe that Earth-based observatories can never achieve. The far side is a naturally shielded radio-quiet zone, and scientists have proposed placing large radio telescopes there to observe the universe at extremely low frequencies that Earth's ionosphere blocks entirely. These frequencies carry information about the early universe, the first stars, and structures that no current telescope can observe. China's Chang'e 4 mission landed on the far side in January 2019, the first spacecraft to do so, and it operates using a relay satellite positioned in a gravitational equilibrium point above the far side that maintains line of sight with both Earth and the lunar surface below. The relay satellite approach works for robotic missions. A robotic rover can wait for signal delays measured in minutes. It can sit still for hours while engineers debate its next move. A human crew cannot do that. An emergency on the far side of the moon means that the crew's first point of contact with any help is a relay satellite. The signal still must travel from the crew to the satellite, from the satellite to Earth, Earth's response back to the satellite, and back to the crew. Total communication round trip, over 2.5 seconds under ideal conditions. During a fast-moving medical emergency or habitat failure, 2.5 seconds per exchange is significant. And if the relay satellite fails, a crew on the far side loses all contact with Earth instantly and completely, with no backup system and no alternative communication pathway. The moon itself is the obstacle, and there is no engineering solution that goes through 2,000 miles of rock. Mission planners considering a far-side crewed mission treat the communication architecture as the first and most critical infrastructure problem to solve. Multiple relay satellites, redundant systems, autonomous emergency protocols that do not require Earth contact to execute. All of this adds cost, complexity and failure points to a mission that is already carrying more risk than any crewed mission since Apollo. No crewed mission to the far side has been formally approved or scheduled. The far side remains, for now, a place where only robots go. But the far side's isolation is a single location problem. The moon's next hazard is a surface-wide phenomenon, embedded in the geology of every square mile of the moon's crust, and it makes the ground itself a trap. The entire surface of the moon is coated in a layer of glass. microscopic, irregular, and embedded in the regolith at every depth. Tiny glass beads and shards cover the lunar surface so completely that it is impossible to pick up a sample of lunar soil without handling glass. This glass was not placed there. The moon made it across billions of years through a process driven by the same micrometeorite bombardment discussed earlier and by the energy of solar wind particles. When a micrometeorite hits the lunar surface at tens of miles per second, the impact energy is so concentrated and so instantaneous that the surrounding rock vaporizes and melts simultaneously. The melted rock sprays outward and then cools in the vacuum so rapidly that it solidifies before the atoms inside it have time to arrange themselves into a crystalline structure. The result is glass, amorphous silica, frozen in disordered chaos, with sharp edges preserved by the absence of weathering. This process repeats across the entire surface, constantly, over billions of years, building up a layer that scientists call the lunar glacier glutinate layer. In some areas, glass makes up more than half of the total regolith volume. For human activity on the surface, this matters in several concrete ways. The glass particles are sharp enough to scratch metal and damage suit materials with repeated contact. The glass surface also behaves optically in ways that affect how the moon reflects light. When you see the moon glowing bright in the night sky, part of that brightness comes from the reflective properties of the glass layer. Light bounces off it from a wide range of angles in a way that solid rock would not, creating a retroreflective effect that makes the moon appear brighter than its average albedo, the formal term for surface reflectivity, would predict. The glass layer also carries trapped gases, solar wind particles, primarily hydrogen and helium, implant themselves into the surfaces of dust grains and glass beads over billions of years of bombardment. These trapped gases represent a potential resource, helium-3 in particular, a rare isotope of helium implanted in the lunar regolith by the solar wind, has attracted scientific interest as a potential fuel for a type of nuclear fusion reactor that does not yet exist but is theoretically more efficient and produces less radioactive waste than current fission reactors. The confirmed resource potential is real. The extraction technology does not yet exist. Processing enough regolith to extract useful quantities of helium-3 would require moving and heating cubic miles of material. The energy cost of that processing, using equipment that must itself be transported to the moon, has not been shown to produce a net energy gain. But the glass layer reveals something deeper about the moon's surface that changes how engineers think about building on it. The surface is not stable. Every new impact adds material, removes material, and rearranges what is already there. The glass record in the regolith shows billions of years of relentless reworking. Structures built on the surface face a substrate that has never been static, and at the micrometeorite impact rate, will continue to be reworked indefinitely. And below the glass and the dust and the loose upper regolith, the ground compacts under pressure in ways that mission planners discovered the hard way, because the compacted layer does something to wheels, boots, and foundations that no one fully anticipated before the missions. The ground grips. And once it grips, letting go is not guaranteed. Lunar regolith looks like loose soil. It behaves like something else entirely. The upper few inches of the moon's surface are loose and granular, easily disturbed by a boot or a wheel. Beneath that, the regolith compacts under its own weight into a material with the mechanical properties of soft concrete. The density increases with depth, and because the particles are angular and interlocked rather than rounded and slippery, they grip each other with surprising strength. Press down on compacted lunar regolith with enough force, and it does not yield the way sand yields. It locks. Apollo engineers discovered this during mission planning, when they tried to model how wheels would behave on the lunar surface. Early rover designs sank into the loose upper layer and then encountered the compacted layer below, creating a situation where the wheel was neither floating on loose material nor rolling on solid ground, but stuck at the interface between the two. The solution for the lunar roving vehicle used in Apollo 15, 16, and 17 was a wire mesh wheel, open-framed and flexible, designed to spread its load across a wide contact area and avoid sinking into the transition zone between loose and compacted regolith. It worked, but the wire mesh design was optimized for flat terrain at moderate speeds. On slopes, particularly slopes covered in loose upper regolith, Overlying the compacted layer, the wheels could dig in, slip, and lose traction. During Apollo 15, the rover drove up slopes steeper than engineers had intended to attempt. The wheels slipped. The vehicle held, but mission controllers watching telemetry from Earth noted stress values on the suspension that exceeded design limits. The crew was told to be more conservative. They acknowledged the instruction and continued exploring. The compaction problem scales badly for permanent infrastructure. A habitat sitting on the lunar surface exerts constant downward pressure on the regolith beneath it. Over time, that pressure compacts the regolith under the habitat's foundation unevenly, because the regolith composition varies across even small areas. Uneven settling causes structural stress in any rigid structure, cracking walls, misaligning door seals, and creating gaps in pressure containment. On Earth, foundations are engineered to deal with settling by going deep enough to reach stable bedrock. On the Moon, the depth of the regolith layer varies enormously by location. In some areas, the bedrock sits a few feet down. In others, the regolith extends over 60 feet before reaching solid material. Without extensive subsurface surveys of a proposed building site, a construction team cannot know what the foundation conditions will look like until they start digging. Those surveys require equipment. Equipment requires launch mass. Launch mass drives mission cost. Every additional piece of site assessment hardware competes for payload space with life support, food, water, and the habitat itself. The compaction problem also affects the most basic lunar construction technique being studied: piling up regolith around and on top of habitats for radiation and thermal shielding. Compacted regolith is a good shield. Loose regolith is a poor one. Creating a reliably compacted regolith shield around a habitat requires mechanical equipment to pack it properly. That equipment, running in a vacuum, on a surface that damages moving parts, maintained by suited crew members with limited dexterity, is a maintenance challenge that mission planners acknowledge but have not fully modeled. And there is one more surface behavior that caught engineers off guard. It happens at a specific moment, predictable on a schedule, and powerful enough to damage electronics that survived everything else the Moon could throw at them. Sunrise on the Moon is not just a lighting change, it is an electrical event, and it arrives fast. Sunrise on the Moon does not warm you gently. It hits you like a switch being thrown, with no atmosphere to scatter incoming light, and no air to gradually warm as the terminator approaches. The transition from lunar night to lunar day is nearly instantaneous at any given point on the surface. The temperature of exposed rock goes from nearly -300 degrees Fahrenheit to over 200 degrees Fahrenheit in the span of a few minutes of solar exposure. That thermal shift alone is violent enough to crack rock, but the temperature change is only part of what sunrise does. As sunlight begins hitting the lunar surface, ultraviolet radiation strips electrons from dust particles and surface materials, creating a sudden and sharp shift in the electrical charge of everything it touches. The transition zone between sunlit and shadowed terrain, the terminator line, carries an intense electric field as positively charged sunlit particles sit adjacent to negatively charged shadowed ones. When sunrise sweeps this terminator across a region, it moves that electric field boundary across every piece of hardware in its path. Apollo-era instruments left on the surface recorded sudden voltage spikes at sunrise and sunset that exceeded the charge levels present during the rest of the lunar day or night. The spikes were brief, lasting only minutes, but the energy involved was enough to cause measurable effects in electronic components. For modern electronics, which operate at lower voltages and with finer circuit structures than the components used in the 1970s, these electrostatic discharge events at lunar sunrise and sunset represent a confirmed hazard. A voltage spike that an Apollo-era component tolerated might destroy a transistor in a modern microprocessor. Engineers designing the electronics architecture for future lunar habitats and rovers treat electrostatic discharge hardening as a non-negotiable requirement. Every circuit must be protected against sudden charge events. Every exposed surface that connects to sensitive electronics must be grounded through the habitat structure. Designing and verifying that protection for thousands of individual electronic components across an entire habitat is an engineering task comparable in complexity to the radiation shielding problem. And the sunrise event does something visible that the Apollo astronauts reported, but that mission planners initially dismissed as an optical illusion. At lunar dawn, just as sunlight begins hitting the surface, some astronauts reported seeing a faint glow or haze near the horizon in the direction of the rising terminator. This was reported independently by several crew members during different missions and was initially attributed to instrument artifacts or visual effects from the helmet visor. Decades later, analysis of the data from dust detectors left on the surface confirmed that the reports were accurate. Electrostatically launched dust particles, kicked off the surface by the charge differential at sunrise, create a brief but real haze of levitated material as the terminator passes. That haze, thin as it is, deposits fresh electrostatically charged dust on every surface it touches. Dust that was carefully managed and minimized over the course of a long lunar night arrives fresh at every sunrise, reset by the electric event, charged and sticky, ready to cling to solar panels, visors, and sensor lenses. The moon resets its dust weapon twice per lunar month, every sunrise, every sunset. And during the long lunar night between those events, the moon's own geological activity produces something that no mission planner added to the original hazard lists, because no one expected a cold, ancient world to be making sounds. The Apollo 17 crew left a heat flow experiment on the surface. It was designed to measure how much thermal energy flows outward from the moon's interior, a straightforward geological measurement. What the instruments picked up, in addition to heat flow, surprised the scientists analyzing the data. Acoustic signals, low-frequency vibrations propagating through the surface rock at regular intervals, timed precisely to the transition between lunar day and night. The moon was cracking. Here is the mechanism. As the surface heats during the 2-week lunar day, rock expands. As the 2-week lunar night begins and temperatures plunge, rock contracts. The thermal swing involved in this cycle, over 400 degrees Fahrenheit, produces mechanical stress in the rock, sufficient to cause fracturing. The surface literally cracks open as it cools and snaps back together, or deforms further as it heats. These fracture events propagate seismic waves through the surrounding rock, waves that the Apollo seismometers and the heat flow experiment detected as crackling pulses. Researchers analyzing the full dataset from Apollo seismometers published findings in 2019 confirming that these thermally driven cracking events occur in predictable patterns tied to the lunar day-night cycle. They are not random geological noise. They are the surface of the moon responding mechanically to the thermal stress it experiences every month, month after month, for billions of years. For a habitat, this matters structurally. Any structure attached rigidly to the lunar rock will experience those same thermal stresses transmitted through its foundation. A habitat that cannot flex slightly in response to the cracking and shifting of the rock beneath it will accumulate stress fractures of its own in its walls, joints, and pressure seals. The engineering response to this is designing habitats with flexible connection points between structural elements, joints that can absorb small movements without transmitting them as stress to the rest of the structure. The concept is well understood from earthquake engineering on Earth. Applying it to a pressurized habitat operating in a vacuum at extreme temperatures, where every joint is also a potential leak point, adds complexity to an already demanding design problem. And the cracking produces one more effect that is easy to overlook, but significant for crews spending months underground: the sounds. Acoustic energy from surface cracking propagates downward as well as outward. A habitat buried under several feet of regolith for radiation shielding would receive a portion of this acoustic energy as low-frequency vibrations in the structure. They would be subtle, probably below the threshold of conscious hearing for most people. But research on the psychological effects of low-frequency vibration on human cognitive performance and sleep quality shows consistent negative effects, particularly on sleep architecture, even at levels below conscious awareness. Long-duration missions on submarines have documented similar issues with low-frequency mechanical noise. The solution on submarines is extensive acoustic dampening in crew quarters. Adding acoustic dampening mass to a lunar habitat increases launch weight. Every additional pound launched from Earth costs money and reduces the payload available for other mission-critical supplies. The moon's geology, its thermal cycling, its crackling skin, its deep and shallow quakes, its active core, contributes to a surface environment that engineers cannot simply park a structure on and walk away from. The ground demands ongoing attention, and the suits that allow astronauts to go out and give it that attention are, on a long mission, deteriorating faster than replacement parts can arrive. A spacesuit is a wearable spacecraft. Every suit used for lunar surface work must maintain pressure against the vacuum, regulate temperature across a range of several hundred degrees, protect against micrometeorite impacts, filter radiation, allow mobility through a pressurized shell, and run all of its life support systems from a backpack small enough to carry. The suits used during Apollo, designated A7L and later A7LB, were engineering masterpieces. They were also single-use, hand-assembled, and designed for a maximum of around 115 hours of combined wear time. After that, the materials had degraded enough that continued use fell outside the certified safety margins. Each suit cost the equivalent of several $1 million in today's purchasing power to produce. There were no spare suits on the moon. If a suit failed catastrophically during a moonwalk, the mission ended. If the failure was severe enough, the astronaut could not return to the lunar module. For a permanent lunar base, the suit problem multiplies dramatically. Crews working outside daily over a year-long mission would accumulate thousands of suit hours across the team. Suits that degrade within 115 hours cannot support that operational tempo. A resupply architecture that ships new suits from Earth every few months is economically prohibitive and logistically complex. The solution requires a suit that lasts hundreds of operational hours rather than tens, that can be repaired on the moon using locally available tools and spare parts, and that maintains its protective performance despite the lunar dust that attacks every seal and joint from the outside. The National Aeronautics and Space Administration awarded contracts to Axiom Space and Collins Aerospace to develop next-generation lunar suits for the Artemis program. Both companies confirmed that dust interaction is the primary durability challenge their designs must overcome. Prototype testing showed dust infiltrating bearing joints within simulated moonwalk durations, shorter than a full Apollo mission. The suits functioned, but the long-term durability data that would certify them for year-long habitation operations does not yet exist. And dust is only part of the suit's enemy list. The electrostatic charge on the lunar surface causes dust to bond to suit fabric at a molecular level. Standard brushing removes surface layers but embeds finer particles deeper into the fabric weave. After multiple moonwalks, suit fabric accumulates a layer of embedded lunar glass that degrades its thermal and mechanical properties progressively. Researchers are developing suit airlocks, small chambers attached to a habitat entrance where a suit can be doffed outside the pressurized interior, preventing dust from entering the living space. This is a promising approach, but adds mass, complexity, and another pressure seal to the habitat design. The most critical moment of any lunar surface operation is the one that gets discussed least in public communications. If a suit fails, the countdown begins. 15 seconds of useful consciousness, perhaps a minute before irreversible biological damage begins. The crew member outside must be rescued and brought inside by the other crew member in their own suit, through an airlock in the time available. Mission simulations have tested this scenario. The results are not reassuring. Every second of every moonwalk, the suit is the only thing standing between a living astronaut and the vacuum. And every hour of every moonwalk, that suit is incrementally less capable than it was at the start. The astronaut inside it, meanwhile, is also changing. And the changes that long lunar stays make to the human body accumulate in ways that do not simply reverse when the mission ends. An astronaut returning from 6 months on the International Space Station needs help walking off the plane. Their legs cannot support their weight without assistance. Their balance system, recalibrated to an environment without meaningful gravity, struggles to process the sudden return of full gravitational load. Their cardiovascular system, which spent 6 months not working very hard to circulate blood against gravity, underperforms under Earth conditions. They sit in a chair on the tarmac and let their bodies remember something they learned in infancy. The International Space Station sits in nearly zero gravity. The Moon offers 1/6 of Earth's gravity. The biological degradation in 1/6 gravity should be slower and less severe than in zero gravity. But slower is not zero. And the specific physiological changes that 1/6 gravity drives in the human body over months are less well understood than the zero gravity equivalent, because no human being has ever spent months in 1/6 gravity. What scientists know from modeling and from animal research in partial gravity is this: bone density loss continues in 1/6 gravity at a rate between the zero gravity rate and the Earth rate. Muscle mass in weight-bearing muscles decreases because those muscles are supporting less load. The cardiovascular system partially deconditions. The vestibular system, the inner ear balance apparatus, recalibrates to the lower gravitational environment over a period of weeks and then must recalibrate again upon return to Earth. Each recalibration takes time. During that time, the system is operating outside its normal parameters. On Earth, a person whose vestibular system is miscalibrated has poor balance, occasional dizziness, and impaired coordination. On the Moon, those same symptoms occurring during a moonwalk or an emergency response create operational risk. There is a cascade effect that mission planners have only recently begun to model quantitatively. As a crew member's physical condition degrades over a long lunar stay, their ability to perform physically demanding emergency tasks, such as carrying an incapacitated crew member, performing manual habitat repairs under time pressure, or conducting an unplanned heavy lift during a rover rescue, decreases. The mission is most dependent on peak physical performance at exactly the moments when that performance is hardest to guarantee. Exercise in lunar gravity partially counteracts degradation, but cannot prevent it entirely. The specific exercise regimes that maintain Earth-compatible physical condition in 1/6 gravity are still being determined. The machines required to run those regimes must be launched from Earth, maintained in a vacuum, and operated by suited crew members if mechanical failures require external repair. And bone density loss carries a specific risk that compounds with the radiation environment. Radiation damages bone marrow, the tissue inside bones that produces blood cells. Reduced bone density means less bone marrow volume. The combination of radiation exposure and mechanical unloading of bones creates a situation where bone health degrades faster than either factor alone would predict. Researchers studying the health data of Apollo astronauts have confirmed elevated rates of cancer and cardiovascular disease compared to astronauts who flew to lower orbits. The sample size is small. The data is suggestive but not definitive. The direction of every data point is consistent with what the physics and biology predict. A crew returning from a year on the Moon would arrive home fundamentally changed in ways that medical science can describe, partially treat, and cannot fully prevent with current technology. And getting them home depends on a launch window. One specific window. Miss it, and the crew waits in the hostile environment they just spent months surviving. Launching from the Moon is not like launching from Earth. On Earth, if a launch is scrubbed, the rocket sits on the pad and waits. The pad is accessible. Technicians can service the vehicle. The countdown can be reset in hours or days. The infrastructure for delay exists at every level of the operation. On the Moon, a crew waiting to launch home is sitting in a habitat with finite consumables, in an environment that is actively degrading their equipment, their suits, and their bodies. Every day of delay costs something real. Days of food, hours of suit life, percentage points of bone density, capacity of the habitat's life support systems to continue functioning without maintenance that requires Earth-based parts. The Lunar Ascent Vehicle, the spacecraft that lifts a crew off the Moon and delivers them to an orbiting vehicle for the trip home, must launch within a window timed to the orbital mechanics of the return journey. The vehicle in orbit waiting to receive the ascending crew follows a path governed by physics, not preference. It appears in the correct position above the landing site at specific times that repeat on a predictable schedule. But if the ascent vehicle misses the window, the next opportunity may be days away. During Apollo missions, the ascent window was tightly constrained. Mission planners calculated backup windows, but the crew's time on the surface was scheduled to ensure they reached the primary window with margin. A major equipment failure that prevented launch on the primary window would have been a serious emergency, with no guarantee of a clean resolution. For a longer mission with a smaller consumables margin per crew member, a missed launch window is categorically more dangerous. A crew that cannot launch on schedule cannot simply wait comfortably. They are consuming resources that were budgeted for the journey home. The ascent vehicle itself is a single point of failure with no backup on the current moon. An orbital space station has rescue procedures, redundant systems, and the option of an emergency return vehicle. A lunar ascent vehicle is the only way off the surface. If its engine fails to ignite, or if a fuel line is damaged, or if a seal fails during the pressurization sequence, the crew is stranded in a place from which no other vehicle can reach them in time. Apollo engineers recognized this and designed the ascent engine with extreme simplicity, a pressure-fed hypergolic propellant system, with no moving parts in the combustion chamber and no igniter required, because the two propellants ignite on contact. The design worked flawlessly on every mission. It also left no room for manual intervention if something outside the simple system failed. Modern ascent vehicle designs for the Artemis program are more capable but also more complex. Every additional capability introduces an additional failure mode. The engineering trade-off between capability and reliability in a system with zero backup options is one of the hardest problems in aerospace design. And even a perfectly executed launch from the moon is only the beginning of a journey home that exposes the crew to the radiation environment of deep space for days before they reach Earth's protective magnetic field. The moon traps you in ways that go beyond physics, and those traps go deeper the longer you stay. 90 days into a simulated long-duration mission, something consistent happens. It has been documented in Antarctic winter-over cruise, in submarine deployments, in confined habitat simulations run by space agencies around the world. Around the 3-month mark, interpersonal dynamics in isolated small groups shift in ways that are predictable, repeatable, and difficult to prevent. Researchers call it the third quarter phenomenon. After the initial novelty of the mission has worn off, and before the final phase when the end is clearly in sight, the psychological weight of the environment reaches its peak. Irritability increases. Sleep becomes less restorative. Motivation for non-essential tasks drops. Small interpersonal frictions that the group managed easily in the first weeks become sources of genuine conflict. Cognitive performance on tasks requiring sustained attention and flexible thinking declines measurably. On the moon, this psychological arc plays out inside a habitat smaller than most studio apartments, with crew members who have limited privacy, no physical escape from each other, and a sensory environment that changes less from day to day than any environment a human being has ever inhabited long-term. There is no walking outside for air. Every excursion outside requires hours of preparation, carries real physical risk, consumes suit life, and must be justified in operational terms. The outside is not a refuge. It is a work environment, hostile and demanding. Communication with Earth is possible, but provides only partial psychological relief. Talking to family and friends through a video link with a one-way delay of over a second helps. It does not replace the neurological and emotional benefit of physical proximity to other human beings outside the mission group. Research consistently shows that isolated crews who maintain strong Earthside communication still experience the same psychological degradation trajectory as crews with limited communication, differing only in the severity of some symptoms. The missions that have pushed human beings into comparable isolation produced remarkable outcomes alongside the documented psychological costs. People adapt. They find rhythms and routines. They maintain function in conditions that would have seemed impossible before they entered them. But adaptation is different from immunity. The documented costs are real and cumulative. Long-duration spaceflight psychology researchers identified 5 factors that determine how a small crew performs under sustained isolation: group cohesion at mission start, leadership structure clarity, access to meaningful work that produces visible results, reliable communication with the outside world, and the presence of what researchers call behavioral health monitoring, ongoing psychological support from mission control. All 5 factors are manageable. None of them eliminate the underlying biological reality that human beings evolved for social environments with dozens to hundreds of familiar people, seasonal variation, physical freedom, and the option to leave a situation that has become intolerable. A lunar habitat removes every one of those options for the duration of the mission. And as the crew manages the psychological weight of their confinement, the moon is doing something to their relationship with Earth itself that no training or communication protocol can fully address. seeing Earth shrink in the sky, day after day, as the people inside that habitat deal with the technical and psychological demands of survival, produces a cognitive shift that astronauts from multiple programs describe in remarkably similar terms. The overview effect is well documented. What happens after the novelty of it fades, and Earth remains visible but unreachable for months, is a territory that only the next generation of long-duration lunar crews will fully explore. And the Moon's relationship with Earth goes deeper than psychology. The physical connection between these two worlds is reshaping both of them, slowly and permanently, in ways that only became clear when scientists started reading the geological record of each. Every year, Earth's rotation slows down by a tiny amount. The day gets longer. Not by much, about 1.5 milliseconds per century. That sounds meaningless. Over geological time, the cumulative effect is staggering. 4 billion years ago, Earth's day lasted approximately 6 hours. The Moon was much closer, orbiting in a much tighter path, and the tidal interaction between the two bodies was correspondingly more powerful. The same gravitational pull that creates ocean tides on Earth is also transferring rotational energy from Earth's spin to the Moon's orbital motion. Earth gives up spin. The Moon uses that energy to move slightly farther away. This is confirmed by direct measurement. Scientists bounced lasers off retroreflectors left on the lunar surface by Apollo missions and measured the round-trip travel time of the light with extraordinary precision. The Moon is moving away from Earth at approximately 1.5 inches per year. The measurement is confirmed and repeatable. 1.5 inches per year sounds negligible. Over human timescales, it is. Over astronomical timescales, it is reshaping the Earth-Moon system in ways that have already dramatically altered both worlds and will continue doing so for billions of years. The slowing of Earth's rotation has direct consequences for the planet's climate and geology. Faster rotation in Earth's distant past drove stronger atmospheric circulation, different storm patterns, and a different distribution of heat from the equator toward the poles. The length of the day shapes everything from ocean current patterns to the behavior of the atmosphere, to the evolutionary pressures on life. Meanwhile, as the Moon moves outward, its tidal influence on Earth weakens. The tides that currently help mix the ocean's layers, driving nutrient circulation that supports marine ecosystems, will slowly diminish over billions of years as the Moon retreats. The ecological consequences of that change operate on timescales beyond meaningful human planning, but they are real physical processes already underway. The retroreflector measurements that confirmed this drift are among the most precise physical measurements ever made in planetary science. A laser pulse sent from Earth hits a mirror the size of a briefcase on the lunar surface and returns with enough precision that scientists can detect the Moon's recession at the millimeter level. Those same measurements revealed that the Moon does not recede at a perfectly uniform rate. There are periods in the geological record, readable in ancient tidal sediments preserved in rock layers on Earth, where the Moon moved away faster, and periods where it moved more slowly. Scientists studying one such period found evidence that roughly 1.5 billion years ago, the recession nearly stalled. The Moon barely moved for tens of millions of years. The mechanism behind this slowdown is still under investigation. The Moon and Earth are a system. They have been shaping each other since the violent event that created the Moon in the first place. And that creation event was so catastrophic that calling it a collision undersells what actually happened. About 4.5 billion years ago, a body roughly the size of Mars struck the young Earth. The impactor is called Theia by scientists, named after the Titan goddess from Greek mythology, who was the mother of the Moon. The collision was confirmed not by observation, but by the physical evidence it left behind in the composition of both worlds. Here is what the evidence tells us. The Moon's overall composition matches Earth's mantle almost exactly in ways that are statistically impossible through any formation mechanism. Except a direct giant impact, oxygen isotope ratios, a chemical fingerprint that varies across different parts of the early solar system, match between Earth and the Moon at a level of precision that rules out the Moon forming elsewhere and being captured by Earth's gravity. The Moon formed from Earth, or from a mixture of Earth and Theia. That is the confirmed scientific conclusion. The impact itself would have been incomprehensible in scale. Theia struck at a velocity estimated between 10 and 25 miles per second. The collision released energy equivalent to billions of nuclear weapons firing simultaneously. Both bodies were largely or completely vaporized and melted by the impact. The material that did not escape the gravity of the resulting combined mass formed a disk of molten rock and vapor, orbiting the hot and damaged proto-Earth. From that disk, the Moon assembled in an astonishingly short geological time, perhaps within a few thousand years. The accretion of material from the disk was driven by gravity, the particles clumping, heating, and merging until the Moon reached something close to its current size. The early Moon was a ball of magma, a global ocean of molten rock that took tens of millions of years to cool and solidify into the crust that now covers its surface. The giant impact hypothesis, first proposed in the 1970s, has been refined significantly as more data arrived. A competing model suggests Theia did not strike at an oblique angle as originally proposed, but nearly head-on, and that the resulting collision was so energetic it effectively vaporized both bodies into a shared cloud of rock vapor that later condensed into the current Earth-Moon configuration. This model, still under active investigation, better explains some compositional similarities between Earth and the Moon, but requires revisions to how scientists understand the energy of the impact. What both models agree on is the violence of the event. The early Earth's surface was completely reworked by the impact. Any chemistry or geology present on Earth before Theia struck was erased and rebuilt from the aftermath. Some researchers have proposed that the impact may have been necessary for Earth's subsequent habitability, that it set the tilt of Earth's axis that drives the seasons, established the Moon's stabilizing gravitational influence on that tilt, and delivered a fresh reservoir of chemical elements from Theia's body that contributed to Earth's eventual capacity to support life. The Moon, therefore, is not simply a feature of Earth's sky. It is a structural component of the conditions that made Earth livable. And what its absence would mean for Earth goes far beyond losing the tides and the nighttime light. Remove the Moon and Earth begins to wobble. Earth's rotational axis is currently tilted at about 23.5 degrees relative to its orbital plane. That tilt is the reason seasons exist. The northern hemisphere tilts toward our star during summer and away during winter. The southern hemisphere reverses. This regular, predictable variation in solar exposure has shaped Earth's climate for hundreds of millions of years and driven the evolutionary development of life adapted to seasonal cycles. The Moon stabilizes that tilt. Its gravitational influence acts as a gyroscopic damper, holding Earth's axial tilt within a relatively narrow range of variation over millions of years. Computer models of Earth's axial behavior, without the Moon's stabilizing presence, show the tilt varying wildly, swinging between near zero and over 80 degrees over periods of tens of millions of years. An axial tilt of near zero means no meaningful seasons. The tropics stay hot, the poles stay cold, and the moderate seasonal variation that drives agriculture, weather patterns, and ecosystem diversity disappears. An axial tilt of 80 degrees means the planet rolls almost onto its side relative to its orbit. Polar regions would receive direct sunlight for 6 months at a time, heating to temperatures incompatible with their current ecosystems. Equatorial regions would experience 6 months of near darkness, followed by 6 months of intense direct exposure. These are not hypothetical extremes. Mars, which has a similar axial tilt to Earth, but lacks a large stabilizing moon, has experienced extreme axial variation over geological time. Computer reconstructions of Mars's past suggest its tilt has swung dramatically across geological periods, likely contributing to the repeated collapse and expansion of polar ice caps visible in Martian geological layers. Without the Moon, Earth's climate would be dramatically less stable over the millions of years required for complex life to evolve. Whether complex multicellular life could have developed at all under those conditions is a question scientists consider seriously. The stable seasonal pattern that the Moon provides may have been a prerequisite for the slow, consistent evolutionary pressure that produced the biological complexity seen on Earth today. The Moon also drives the ocean tides, and the tidal zones, the bands of coastline alternately covered and exposed by rising and falling water, created one of the most evolutionary productive environments in Earth's biological history. The regular cycling of exposure and submersion at tidal zones drove adaptations in early marine life that eventually led to the colonization of land. Remove the moon and the tides become driven only by the gravitational pull of our star, which still creates tides but much weaker ones, reducing the intertidal zone's productive variability dramatically. The moon, the world we are planning to return to, the surface hostile enough that no human has stood on it in over 50 years, turns out to be a structural necessity for the planet that produced us. And every plan to establish a permanent presence on that surface collides with a final, compounding set of problems that engineers and scientists are only now beginning to describe honestly. Every challenge described in this video compounds with every other one. That sentence matters. Individually, many of the problems on the moon have partial engineering solutions. Radiation shielding reduces radiation dose. Dust mitigation reduces dust contamination. Underground construction reduces thermal stress and micrometeorite damage. Better suits extend surface operation time. Nuclear power removes the dependency on sunlight. Each of these solutions exists in some form, at some level of development. The problem is that applying all of them simultaneously, in the actual environment, with the mass constraints of existing launch vehicles, with crews whose physical and psychological condition is changing over time, produces a complexity that no single engineering team has yet fully modeled end to end. Consider the mass problem alone. A lunar habitat capable of housing 4 people for 1 year, with adequate radiation shielding, structural redundancy for moonquakes, thermal management for the full lunar day-night cycle, dust mitigation at every airlock and exterior connection, life support capable of recycling air and water, with Earth-standard reliability, power from a nuclear source, plus backup solar, medical equipment for common emergencies, food for the full mission duration, plus the tools and spare parts to maintain all of these systems when they inevitably require maintenance, adds up to a launch mass that exceeds the capacity of any single rocket currently in operation. The National Aeronautics and Space Administration's Space Launch System, the most powerful American rocket, currently flying, can deliver about 95,000 pounds to lunar orbit. Estimates for a minimum viable permanent lunar habitat, including all the systems listed above, run between 2 and 5 times that mass. That means multiple launches, precise orbital rendezvous, assembly operations conducted in lunar orbit or on the surface, and a supply chain that must run without interruption for the duration of the mission. Each supply launch from Earth takes days of transit time, costs hundreds of millions of dollars, and depends on a launch window that the physics of orbital mechanics determines. A component that fails on the moon cannot simply be replaced by ordering a spare online. The replacement must be designed, manufactured, tested, packaged, for launch launched, transited to the moon, and delivered to the surface. That pipeline takes months minimum and could take years for specialized components. Scientists and engineers working on the Artemis program, the current framework for returning humans to the moon, are explicit in their public communications about these challenges. The program is building toward a sustained presence incrementally. Shorter missions first, longer ones later, with each mission adding to the surface infrastructure and expanding what future missions can rely on. The Gateway space station, planned for lunar orbit, adds a staging point for surface operations and an emergency refuge in the event of a catastrophic surface emergency. This is the serious, careful approach, and it acknowledges, implicitly, that a permanent lunar base is not a near-term reality. It is a long-term goal that requires solving problems that have not yet been solved, with technology that has not yet been built. On a timeline measured in decades, the moon is close enough to see with the naked eye. It is far enough away, and hostile enough in every dimension, that humanity's return to its surface is one of the most demanding engineering projects our species has ever attempted. And every step toward that return reveals a new layer of what the surface is actually doing. The moon was supposed to be geologically dead. That was the consensus before Apollo. A small rocky world, cold through to its core, seismically silent, without the internal heat engine that drives volcanism and plate tectonics on Earth. The moon's small size meant it should have lost its internal heat billions of years ago. Small bodies cool faster than large ones, the same way a marble cools faster than a boulder. The Apollo seismic data changed that understanding. and left questions that scientists are still working through. The deep moonquakes, occurring 700 miles beneath the surface on a schedule tied to Earth's tidal pull, require something in the moon's interior to be warm enough and plastic enough to respond to that tidal stress. Completely cold, rigid rock does not produce rhythmic deep quakes. It produces random fractures. The rhythmic, predictable quality of the deep moonquake pattern tells scientists that the material generating those quakes is responding elastically to periodic stress, which means it retains some capacity for ductile deformation. Completely solidified rock does not do that. Analysis of the full Apollo seismic dataset, combined with more recent data from the Lunar Interior Temperature and Materials Suite carried by the Chang'e missions and from gravitational mapping by the Gravity Recovery and Interior Laboratory spacecraft, confirmed that the Moon has a small iron core surrounded by a partially molten layer called the mantle transition zone. Partially molten, on a world that was supposed to be cold and dead billions of years ago. The source of the residual heat keeping that interior partially liquid is still debated. Radioactive decay of elements concentrated in the deep interior contributes. Tidal heating from Earth's gravitational pull contributes. Whether these two sources alone account for the observed thermal state, or whether some additional heat source is operating, remains an open scientific question. The partial melt in the lunar interior also means that the Moon is not perfectly rigid. It flexes. The tidal forces from Earth cause the Moon to deform slightly as it orbits, and that deformation dissipates energy as heat. Scientists measuring the degree of this tidal flexing from orbital data found values consistent with a partially liquid interior. The numbers work. The Moon is measurably squishy at the level of precise orbital mechanics. This matters for lunar base planning in a specific and underappreciated way. A partially molten interior, even a small and deep one, maintains the potential for geological events that a fully solidified interior would not. The shallow moonquakes, the ones powerful enough to qualify as major earthquakes in terms of energy release, draw their origin from the same thermally active interior that the seismic data revealed. A world with residual internal heat is a world that will continue expressing that heat through geological activity. The Moon is not as dead as it looked from Earth, and its living interior generated the event that may explain one of the stranger features visible on the lunar surface, the vast dark plains called Maria, which formed from volcanic eruptions that occurred billions of years ago and left behind smooth, dark basalt plains that you can see from Earth with the naked eye. The Moon had volcanoes for billions of years, and the last of those volcanoes may have been active far more recently than scientists originally believed. The dark plains on the Moon's near side are ancient lava flows. This is confirmed geology. Between 3 and 4 billion years ago, the lunar interior was hot enough to produce large-scale volcanism. Magma erupted through cracks in the crust, flooded the floors of large impact basins, and solidified into the dark, relatively flat plains that give the Moon its recognizable face. The lava flows filled basins hundreds of miles across and reached depths of several miles in some locations. When you see the man in the Moon, you are seeing the solidified remnants of an ancient volcanic era. The accepted timeline had volcanism ending roughly 3 billion years ago, as the interior cooled past the threshold needed to sustain eruptions. Then a team of scientists reanalyzed high-resolution imagery from the Lunar Reconnaissance Orbiter and found something that upended that timeline. Small volcanic deposits covering areas of a few square miles rather than hundreds, scattered across the near side and showing geological characteristics inconsistent with ancient origin. The deposits lacked the crater density expected of 3 billion-year-old surfaces. Features eroded by the micrometeorite bombardment at the expected rate should show a measurable crater population after 3 billion years of exposure. These deposits showed far fewer craters, consistent with surfaces tens of millions of years old, rather than billions. The features were named irregular mare patches, and their implied age, somewhere between 30 and 50 million years old, means that the Moon may have experienced localized volcanic activity within a geological timeframe. That, on cosmic scales, is essentially recent. 50 million years ago, the ancestors of modern whales were walking on land on Earth. By geological standards, that is yesterday. The irregular mare patches may represent the Moon's most recent volcanic exhale, small final eruptions from a dying volcanic system. Or they may represent a category of activity that occurs more frequently than the large ancient eruptions and has been happening in small-scale episodes throughout the moon's history. Scientists studying the patches confirmed that they are real geological features with real age implications. What drove them, and whether the mechanism that produced them is fully exhausted or still capable of producing future events, is an open question. A future small-scale volcanic event on the moon would not be catastrophic in the way Earth's large eruptions are. The volumes involved are small, the effects would be local. But for a lunar base positioned near one of these potentially active zones, local effects include outgassing from the surface, which can change the local vacuum environment and introduce chemical contaminants into the habitat's exterior. It includes thermal anomalies that affect ground temperature and stability, and it includes the seismic activity that accompanies any volcanic process. The moon's geological story is longer, stranger, and more active than the cold, dead world of pre-Apollo expectations. Its history began with the most violent event in Earth's neighborhood since the planet formed, and the reverberations of that history are still playing out in ways that a crew living on the surface would need to account for every day. The final picture that emerges from everything on this list is one that scientists and engineers are beginning to state plainly in public forums, where not long ago, the framing was always more optimistic. Here is what a lunar base actually requires to be genuinely sustainable. Radiation shielding that reduces the surface dose to levels compatible with long-term human habitation. Power systems that function through the 2-week lunar night without dependence on sunlight. Dust mitigation at every interface between the inside of the habitat and the outside environment. Life support systems that recycle air and water with near-perfect efficiency over years, without Earth-supplied replacement parts. Medical capability sufficient to handle emergencies that would require hospital treatment on Earth. Communication architecture that provides reliable contact with Earth and cannot be eliminated by a single point of failure. Structural design that survives thermal cycling, moonquakes and micrometeorite accumulation over years. Launch and landing infrastructure that does not contaminate or structurally damage the habitat and surrounding equipment with every supply delivery. Each item on that list requires technology that either does not yet exist in operational form, has been demonstrated only in laboratory conditions, or has been tested in space environments that are less extreme than the lunar surface. The gap between what is required and what currently exists is not a gap that clever engineering alone closes quickly. It is a gap that requires years of development, testing in the actual environment, iteration based on failure, and a sustained financial commitment that no space agency has yet formally committed to maintaining over the required timescale. This is not pessimism about human capability. The history of what human beings have accomplished in aerospace is one of the most remarkable records of problem solving in the history of the species. The people working on these problems are doing so with intelligence, creativity, and genuine dedication. The solutions are coming. They are simply not here yet. What is here is a clear understanding of the problem that was not present before Apollo. Before those missions, the moon was an unknown. After them, it is a known hostile environment with a specific and documented list of threats. The Apollo program succeeded in the most important thing it could have accomplished. It gave us accurate information about what we are up against. NASA's Artemis program is working through the list methodically. The Gateway Lunar Space Station, currently in development, provides an orbiting refuge and staging platform. The Commercial Lunar Payload Services program is delivering robotic precursor missions to the surface to test technologies and characterize specific sites before crews arrive. The Human Landing System, contracts with SpaceX and Blue Origin, are developing vehicles capable of transporting crews to and from the surface with greater payload capacity than the Apollo lunar module. All of this is real, funded, and in various stages of development. The first crewed Artemis landing, delayed multiple times from its original schedule, represents the next human footsteps on the moon and the beginning of a new phase of understanding what sustained presence actually requires. The moon is survivable in the near term. The evidence from Apollo confirms that. Whether it is survivable in the long term depends on engineering and biology questions that are only answerable by doing it and measuring the results. Every problem the moon presents has a counterpart on every other body in the solar system that humans might one day visit. The radiation environment on the Moon is severe. The radiation environment on Mars, which also lacks a global magnetic field, is comparable. The radiation environment in deep space between planets is worse than both. Solving the radiation problem for the Moon does not fully solve it for Mars, but every protective technology developed and tested on the Moon advances the state of the art for everything that follows. The dust problem on the Moon is uniquely tied to the Moon's specific geological history and the absence of weathering. Mars has dust too, different in composition, less glass-edged, but present in quantities sufficient to cover entire hemispheres during global dust storms. The dust management systems developed for lunar operations will need adaptation for Mars, but the engineering knowledge transfers. The life support challenge of recycling air and water with high efficiency in a closed system is a challenge for every mission beyond low Earth orbit. The International Space Station's life support systems achieve roughly 90% water recycling efficiency. A lunar base needs higher. A Mars base needs higher still, because resupply timelines are measured in months rather than days. Every percentage point of improvement in closed-loop life support developed for lunar operations directly reduces the risk of a Mars mission. The psychological challenge of small crew isolation in a hostile environment is a challenge for every deep space mission. The data collected from lunar crews over extended stays will be among the most valuable behavioral health datasets ever assembled, informing crew selection, mission design, and psychological support protocols for every mission that follows. In this sense, the Moon's hostility is not just a problem, it is a curriculum. Every challenge it presents is a lesson that, once learned on a world 2 days from Earth, becomes a survival advantage for missions orders of magnitude farther away. The physicists, engineers, physicians, and psychologists who spend their careers on the Moon problem are, whether they frame it this way or not, building the knowledge base that determines whether human beings can live anywhere other than Earth. The Moon is close enough to matter as a test environment and hostile enough to make every test meaningful. It punishes shortcuts. It exposes gaps in planning with immediate physical consequences. It is the universe's harshest and most accessible classroom. And what the people studying it most carefully have concluded, looking at everything on this list, everything confirmed and measured and documented across decades of research and 6 crewed landings, is both sobering and galvanizing. The Moon can be survived, long-term, permanently, with technology we are capable of building, on a timeline we are capable of meeting if the commitment remains consistent. The path forward is harder than optimistic public statements have sometimes made it sound. The people walking that path know exactly how hard it is, and they are walking it anyway. Every reason to avoid the Moon leads back to a more important reason to face it. The radiation will damage any crew that stays too long. So scientists are developing shielding and pharmaceutical countermeasures and operational protocols that reduce the exposure to manageable levels. The dust will destroy equipment and invade lungs. So engineers are building suits, airlocks, filtration systems, and electrostatic repellers that slow its advance. The 2-week night will kill any solar-powered system. So nuclear reactors, small enough to launch and powerful enough to sustain a habitat, are moving from design to test hardware. The Moon resists, humanity responds. That dynamic is as old as exploration itself, and the Moon is simply the most honest version of it that this generation has access to. There is also a strategic reality that makes the Moon unavoidable as a destination, regardless of its difficulty. The Moon contains water ice, confirmed in quantities that can support a propellant production facility. Hydrogen and oxygen extracted from that ice can fuel rockets. A fuel depot in lunar orbit, supplied from the lunar surface, would change the economics of deep space exploration the way refueling stations changed transcontinental travel. Every mission to Mars, to the asteroid belt, to the outer planets, becomes cheaper and more capable if it can refuel at the Moon rather than carrying all its propellant from Earth's gravity well. This is the strategic vision that drives serious long-term planning at every space agency and an increasing number of private companies. The Moon is a stepping stone, not a destination for its own sake, but the first essential rung on a ladder that goes much farther than the Moon itself. China's lunar program is advancing with a stated goal of crewed landings before the end of this decade. The European Space Agency has supported the concept of a multinational lunar village as a long-term goal. Private companies with launch vehicles capable of reaching the moon are proposing commercial resource extraction as a business model. The moon is entering a period of increased human attention from multiple directions simultaneously. What every one of these programs will encounter, the moment they put people on the surface for more than a few days, is the complete and unedited version of what this video has described. The dust, the radiation, the temperature, the silence, the seismic instability, the psychological weight, the biological cost, the engineering demands. The moon does not soften its reception for optimism or good intentions. What the people going back will have that Apollo did not is knowledge. Precise, confirmed, painstakingly gathered knowledge about every hostile thing the moon does and how to minimize each one. They will go in with eyes open to the difficulty, equipped with technology built specifically to address confirmed threats, rather than guessed ones. Apollo astronauts describe the moon as a place that wanted them dead. The astronauts who follow them will know exactly why, and exactly how to survive it anyway. The moon is the most hostile place any human being has ever stood. It is also, right now, the most important place our species needs to learn to live. Humanity has survived every environment it has decided to inhabit. Deserts, deep ocean floors, polar ice. It will survive this one too. The surface is waiting, the preparation is underway, and the distance between where we are and where we need to be is exactly the kind of problem that human beings are, it turns out, built to solve.